Exponential Forces of Technological Change, Moore's Law and More Laws. And our speaker is going to be introduced by Professor Dan Roos of MIT. You can read his very impressive bio on the handout, but it's very appropriate that he's here today and introducing our speaker. He's the founding director of MIT's ESD, Engineering Systems Division, and for that we owe him a great deal of thanks and gratitude. Dan?
We just heard an amazing talk from somebody who's had a very, very distinguished career. Now we're going to shift somebody who really is starting out on their career. Jessika Trancik is the Atlantic Richfield Career Development Assistant Professor of Energy Systems in the Engineering Systems Division at MIT. She got her PhD at Oxford. After getting her degree, she served as a fellow at the Santa Fe Institute and also at the Earth Institute at Columbia University. Her research is really looking at, I think, what she refers to as informed innovation. How do you accelerate the development of technologies, doing it in a way in which you're conscious about a lot of the factors, in particular, what the environmental impact is going to be, the sustainability question, and also the cost question. And she's focused primarily in the area of energy systems, looking both at electrical energy and transportation. So it's my pleasure to introduce Jessika.
Okay, thank you, Dan. Okay, great. So I'd like to talk about exponential forces of technological change. And technology development can be a lot like the picture here of this control panel, whether you're an individual in the lab, a government investing precious public funds in R&D, or a firm. And the question is, which knobs should we turn in order to improve technologies? What we do in my research group is to harness information in large data sets in order to try to understand the reasons behind technological improvement, the impacts of technologies, so evaluate environmental impacts ex ante, in order to inform design in the lab and investment. And as was mentioned, we work on energy technologies in particular, but find that by evaluating a broader set of technologies, we can learn important general lessons. And one of my major areas of interest is in understanding how technologies change and improve over time and how we can use the past to inform the future. And this is what I'll discuss today. One measure of technological change is prevalence, shown here for transistors, how that's changing over time, the growth in transistors. Note the log scale, the log y axis there. And what we've seen in transistors is a doubling of production every 1.2 years. So really rapid growth in transistors. Another measure of change is technological performance improvement. Here I'm showing an example of Moore's law applied to the cost decline in transistors. And what we see here again is really fast rates. Now we're looking at rates of improvement. a halving time of 1.4 years. At these rates of improvement, let's take the example of how fast we all run. So if I took the average speed, the running speed of everyone in this room, any one of you would break the world record within 2 years if you improved this quickly, right? So really rapid rates of improvement, 20 to 30% across the IT technologies. And this led to Bill Gates stating, as shown here, that we've been spoiled by Moore's law. And then going on to say that a few areas of technology will enjoy exponential growth, but other segments will grow and improve more slowly. So this is what I set out to test in the paper that I'll talk about briefly for a few minutes. And then we'll talk more generally about some of the implications for service industries. So in this paper, what we did, and this paper is posted online on the conference website in case you're interested, was to collect data on 100 technologies. This is actually not easy to do. 100 doesn't seem like a large number, but this data isn't very readily available. So this took a lot of sweat and tears, some of my own, some of my students. And then we tested 6+ theories. One of them is Moore's law. We actually started out looking at 14 theories. There's a lot of theories out there as to how technologies improve over time. We ended up zeroing in on these 6 because the others performed very poorly. But Moore's law is one of these theories. So taking all of these 100 technologies, we then looked at how well these different laws do in forecasting future performance. Measuring that by using something called hindcasting, which gives us an error mountain for each one of these technology law pairs. And what we see in general is that as you forecast further into the future, you see an increasing error. So you move up that error mountain. And looking at all these combinations of technologies and laws led to about 40,000 error data points. So we had a lot of these error mountains here projected on a 2D surface. So we needed then a statistical model to interpret the results. And the important aspect here is to pull out the effects due to the data sets, which we're treating as random, and the effects due to the functional form, to the equations. And the bottom line is what we found is that, in fact, Moore's law does quite a good job of predicting future improvement. This is the case across many technologies. I'm showing the example here for photovoltaics. It is the case that we see faster improvement in information technologies than in other technologies, but this exponential improvement is actually ubiquitous. It's very prevalent. And this also then allowed us to develop a forecasting model. And importantly, we're able to use information from a lot of different technologies to improve the forecasts for single technologies. So Moore's law is not just for computers. And this was an article on the paper that we wrote that came out in Nature. And I thought the author put it very well. Moore's law is not just for computers. So that's interesting from a fundamental perspective, and we've gone on to look at mechanistic models to explain why Moore's law is so prevalent. But also from an applied perspective, this is important, because getting the right answer has huge implications, and I'll talk about an example just briefly, which is international climate negotiations. Understanding the rates of technological change, understanding the degree of predictability, taking information from the past and using that to inform decisions about the future has very large implications for these questions. And what we're seeing now is, and this paper featured, some of this work featured in this report that came out recently on the new climate economy that came out early in the fall and contained some of our results on these technological trends, making the point that these rates of improvement really need to inform international climate negotiations. And when you look at this problem from a technology lens, it actually doesn't look so bleak, because we're seeing very high improvement rates of these technologies. Now, it doesn't mean we can just sit back and do nothing, but we're actually at a really critical point in the development of these technologies. And I think, this is interesting. It's entering into these international debates. We just had a few weeks ago a commitment by the presidents of China and the US to emissions reductions and emissions plateauing, or an emissions peak in the case of China. So this is important, and for those reasons, and this exercise, sort of, if we step back and think about this exercise, it reminds me of a book by a colleague of mine from the Santa Fe Institute, Duncan Watts, where the title is "Everything is Obvious," right? And this is the case in many real-world problems. It's very easy for people to observe and construct explanatory stories, but it's important to find the right answer. So that asterisk is quite important. Everything is obvious once you know the answer. It can be very important to find the right answer in these big social problems. And in this case, in the example I showed, it's important for the future of the planet. We've gone on to look at design features that can help us predict the rate of change. So there are common design features across technologies captured in a design structure matrix that help us predict the rate of change. We've also identified features like the degree to which technologies are commodity-like, and more commodity-like technologies can slow improvement. And in general, the conclusions from this study show that many technologies follow exponential improvement trends. So many technologies actually follow Moore's law. And recognizing this has allowed us to develop a forecasting model to save public and private money, also led to some results that are contributing to informing international climate negotiations. Importantly, information technologies show unmatched rates of improvement, faster rates of improvement, getting to 20 to 30% rates of improvement. In energy, we have much slower rates of improvement. Photovoltaics is an interesting one. It's improved faster than any other energy technology in the history of the modern energy conversion industry, with rates of improvement at around 10% per year. But most energy technologies improve at slower rates. And then, we can look at other more commodity-like technologies. They improve even more slowly, but they all follow these exponential trends. And we can use simple design features to help predict the rates of improvement. We can never perfectly predict the future, and that's why it's important to really harness large data sets to predict not just our expected behavior, but also the expected error in our predictions. And in this research approach, it's a sort of proof of principle, I think, in that we can harness data on many technologies to improve the development of single technologies. So I've talked about energy, the case of energy, and service industries within energy. But I'd like to step back and just finish up my brief remarks to think about service industries more generally. So one of the things that this research has led me to conclude is that we live in a log world, right? These exponential improvement is all over the place. This has really important implications, I think, for the future structure of our economy, the availability of jobs, the nature of those jobs. And of course, those are not questions that any one of us from any single discipline could address alone. What's really exciting about this meeting is that, it's just speaking with a number of you over the last couple of days, it's bringing together people with very diverse backgrounds, but I think with some common objectives, which is very interesting. And so I wanted to end with some questions that have come up for me in doing this research, and then also considering the expertise in the room. We might ask whether these big questions could be tackled by large interdisciplinary teams if you got the right people together. Some of these very challenging questions could perhaps be tackled. And there are important implications for the service industries of these exponential trends. Questions like, can we plan for technological change? Can we design for system performance? So not just for the performance of small systems, human-computer systems, very important, but also sort of at the societal level. Can we induce technological change to reduce environmental impacts? And can we plan, this is a really big one, plan for the implications for jobs, the nature of jobs, the kinds of jobs that will be available to people, and wealth distribution, given that there's this technological improvement really means that those jobs are becoming more and more skilled, requiring more and more skills going forward. How do we deal with that? If we don't do anything, it has rather, potentially rather, serious and negative implications for jobs and wealth distribution and so forth. And so, as academics, we're not social planners, but it is important, I think, to inform these broader debates with rigorous and also open-minded research. So thank you so much for your attention.
We have time for a few questions. Well, why don't you wait for a mic?
In human systems where people are using technology, there's also these learning effects where the performance, quality, and number of operations get better with the number that you've already done. But that always shows up with diminishing returns. The quality and speed with which you can do a shoulder surgery gets better the more the team does it, the more technologies it uses, but with diminishing returns. So every doubling of the operations is what leads to improvement, not time by itself. So how do you factor, given we're talking about services that require not just kind of the hardware, but this person hardware system, how do you use your kind of models to forecast or understand kind of service productivity, not just technological improvement?
Right, yeah, it's a good question. So, one thing I'll note is that the kind of model that you're talking about is something called Wright's Law, and so I've looked at that as well. It turns out that it's consistent with Moore's Law if the number of improvement attempts is growing exponentially with time. Now, for human systems, we can debate whether that is possible. It's not quite, because we're not growing, the number of people is not growing that quickly. The hours in the day are not changing. So I think that's a really perceptive comment. So I think if we looked at human performance, we would see, we would see, and people have seen in the literature, slower rates of improvement. Now, I think you're asking what to do about that, and I think humans working with technology is really, that's sort of what forms the basis for exponential economic growth and growth and productivity that we've observed for so long. I think these are important issues, and I don't have an answer for it, but I think. They're understanding that difference, the difference in the rate and the difference in the functional form between technologies and people is very important for planning, for the future, at least understanding how the world might change in the future. Yeah.
Jessika, thanks for a fascinating presentation, and I've got two questions. One is, what's on a log curve that would surprise us that maybe we don't know because you looked at many things? So I'm curious what you thought was the most interesting thing on a log that we might not know about. And then conversely, is there something that you can think of that's not on a log curve, but if it was, it would change everything?
Okay, well, I think the first one, we looked at a number of chemicals, so those are shown here. And really, in work that I'm doing right now, we're breaking technologies down into two common components. One is usage rates, and the other is prices. So technology costs, usage rates, and prices of those inputs. And with this model, it's a very general model. I think we can explain a lot of the differences in the rates of improvement. one of the surprising things was that indeed some of these chemicals do show exponential improvement, and that is because these usage rates are changing over time. That's my hypothesis. They show much slower rates of improvement. Now, gosh, what would change the world? Storage technologies. I mean, I work a lot on energy. If we had really cheap storage technologies right now, it would really change what's possible in energy, not just in electricity, but also the transportation sector, because costs of photovoltaics and wind, which are intermittent sources, are low enough now to be competitive at small scales, but you can never get to a majority market share with these intermittent sources. You need storage. So if that took off, there's a lot of people working on. I think Dick Larson talked about different performance metrics and different things that consumers care about and industries care about. So there's a lot of people working now on stationary storage. We've typically designed batteries so that we can carry them around, so they're light, because they go in our electronics, they go in our vehicles. But if we don't have to carry them around, it opens up a lot of opportunities for different chemistries and different materials that we can use to store energy, and also different fundamental, different physical processes as well. So that's an exciting area.
Hi.
One over there, too.
So in your experience, you've indicated that exponential growth brings with it many new opportunities. Does it also bring similarly exponential problems in terms of failure, in terms of where things can go wrong, and
Yeah.
new, as you miniaturize certain technologies, new forms of failure can occur. Mm-hmm. And you have large numbers of devices that are capable of monitoring humans. These devices can fail, and as society tends to get dependent on these new technologies and its growth, are there new vulnerabilities that we expose ourselves to?
Mm-hmm. Well, I'm sure there are. I don't work on that particular question, but as sort of maybe a trivial example comes to mind, which is our dependence on cell phones. The quality of service has probably gone down for a lot of us. The quality of sound and the experience of making a phone call has gone down. But cell phones took off, and there's sort of no going back. But that's kind of a trivial example. I think you're talking about much more, maybe. Although I think, in my group yesterday, we're talking about the aging, and I think that could be a not so trivial example for the aging. Like, as we move to more advanced technologies, a certain portion of the population could be left behind, and that could be a concern. But one thing I want to point out, so I think we could think of a number of examples. I don't myself work on failure of systems, but I think that's a really important point. One example that does come to mind that I want to point out is that really, exponential growth and improvement in technologies is also, of course, part of what is behind the economic growth trends, which are also leading to, together with, wealth per capita together with population growth, together with the demand for modern energy services to provide, a high standard of living, is really leading to increasing carbon emissions of other greenhouse gases, and so that's a really big problem in the energy area. Depending on your tolerance for risk, a lot of us are quite scared of climate risks going forward. So that's interesting, because that's sort of pushing us in the direction of trying to guide innovation in such a way that the performance metrics like carbon intensity of energy, emissions per unit energy, try to bring down those numbers in such a way that you can reduce emissions but also still have cheap energy. So there's a lot of challenges presented by those exponential growth curves.
Jessika, let me ask you a question. When we look at service systems, a lot of the systems consist of mixed technologies that are coming together. And if you look at automotive, for example, we see information system, electronics playing more and more of a role being implemented in traditional automobiles, as contrasted, let's say, to what Tesla has done, where he said, okay, let's step back and let's redesign the car, thinking of it more from a computer system point of view in terms of the design as opposed to the traditional automotive design. Have you looked at those sort of questions where it's a question of you have something and you're making incremental change to it as opposed to taking a step back and saying, we're going to do this thing now from a clean sheet. Mm-hmm. And of course, what we've seen is that the Tesla vehicle is more highly rated than the traditional automobiles, forgetting even the environmental aspects just as a vehicle.
Yeah. So, I'll just share some thoughts on, the general topic. If we go back to this model, which I think explains a lot about prices and usage ratios, sort of combining to determine the cost of a technology. But then we can also think about, at a given cost, usage ratios determining the performance of a technology. Usage ratios as well as the design of the technology itself and sort of how optimized that is. But I think certainly by starting out and designing the entire system, there should be opportunities, based on the work I've done, there should be opportunities to design such a system to improve more quickly. And I think that's part of what we're seeing with Tesla. There are, on the other hand, with Tesla, with switching to another energy source, there are challenges with integration in the existing system, right? Anytime you're designing a technology, you're having to integrate it into a parent system. That's something Ollie DeVec has done quite a bit of work on. So there are more challenges there, and that's due to this change and change from the internal combustion engine and gasoline to liquid fuels to electricity. And then also, what we see with some of these more advanced products, like batteries, solar cells, there's a concern about the materials that we're using for those, because we've moved toward some more exotic materials that give us the performance we want, and now we're having to go back and say, okay, how do we actually go to more common materials, so bring down those prices, but still achieve the same performance. So in some ways, I see it as it's a little bit of a different kind of engineering where you're not trying to do something different for the first time. You're trying to do what you already know how to do, but more cheaply. So it's interesting challenges.
Okay, once again, let me thank Jessika. And Dick, how long should this break be?
15 minutes.
Okay, thank you, Jessika.